chairs when the music stopped. Hopefully everyone could hear the music. We will get the program started again. So I will turn things back over to Jana to introduce our next presenter.
Thank you, Jessamine. Our next speaker is Gary Hunt, and Gary is the Vice President and Technical Director at TRC. He's also an internationally recognized expert on persistent organic pollutants and other emerging contaminants. He is a subject matter expert on PFAS in the atmosphere, including measurement, distribution, occurrence, and transport and fate, and has authored more than 125 journal manuscripts and symposia presentations. And today, Gary's topic is PFAS monitoring in air. And thank you for joining us, Gary, and the stage is yours.
Thank you, Jana, for the introduction. Can everyone hear me? Okay. This morning, we're going to talk about monitoring of PFAS in ambient air. We've heard some of that already from the prior speakers. And I'm going to talk about methodology. I'm also going to look at some data, our data, as well as others, and also behavior of PFAS in ambient air. That topic was touched upon earlier, but I'm going to explore it a little deeper. Next slide. Regarding ambient air monitoring methodology, reference was made to passive sampling techniques such as using polyurethane foam or puff and sorbent-impregnated puff. XAD4 is one example. And then there's active sampling techniques, high volume and low volume, using XAD sorbent, such as with EPA method TO13A, which is a methodology for PAHs in ambient air, and then a sandwich or a combination of puff and XAD for a collection of a variety of semi-volatile organics. Next slide. What we're going to talk about here is TRC embarked on a methodology development or validation, I should say, program in conjunction with Eurofins Test America to come up with a methodology that we could use for collection of PFAS, a variety of PFAS in ambient air. The reason being there's really an absence of the standard method or a TO method or a federal reference method at the present time. So we participated in a jointly sponsored and self-funded program. Initially, there was a pilot study that was using existing EPA sampling and analysis procedures that were adapted to PFAS measurements in ambient air. And then lastly, we wanted to apply a methodology for measurement of PFAS existing in a number of locations in the continental U.S., and I'll be showing you some of that data as well. Next slide. There's the target list that Eurofins use. There's about 32 compounds here. I won't go into them because, as you all know, the chemistry of PFAS is very complicated. And I'm a chemist, and I can tell you it's the most complicated class of compounds that we've ever really encountered in the environment. These are our target analyte list. Next slide. As I said, we selected the high-volume ambient air sampling technique, EPA method TO13A. I'm very familiar with this method. It's used for PAHs and other semi-volatiles, and I'm happy to say that I'm actually referenced in the method at the end for some work we did with PAHs back in the 80s. Design considerations for the method: there was going to be a glass fiber filter or quartz filter for collecting particulate. We looked at a number of solid sorbents, puff, XAD for vapor phase, gas phase. Filters and sorbents were pre-cleaned and proofed in the lab. There were field trip blanks, method blanks. It's important to assess artifacts in the media, as well as contaminants potentially introduced or sample handling in the field. And then the adaptation of the method was to use isotopically labeled PFAS as field surrogates, both spiked in the trap set before they went out into the field, as well as back in the lab to assess recovery of the native compounds. And this essentially would quantify the accuracy of the combined sampling and analysis procedure. One thing I want to point out, and I'll go over it a number of times during this presentation, is contamination from PFAS is a very important thing to address. It's going to be there. If you don't see it, you're doing something wrong. Your key or your main objective is to reduce the level of contamination so that you can get a reliable measurement on the native compounds in ambient air. Next slide. We adapted a number of other quality control measures. Co-located samples were used in all cases. We didn't take just one sample. There were two, some cases more. Redundancy as an insurance policy in the event that the field event is aborted or the data from one sample is invalid. And it provides precision of the combined sample collection and analysis procedure. Our analysis was done by isotope dilution, LCMS, and our objectives were to get detection limits that were matrix dependent, compound specific, and see what the influence of blanks would be on those detection limits. Next slide. We used one of the sorbents we used was a high volume air sampler sorbent module with PUF XAD, as you can see in this particular photo. We got PUF and XAD in this glass trap. Next slide, please. These are not samplers from our program, but I just wanted to illustrate that these samplers are used often for collecting semi-volatile organics and ambient air. On the left, there's a program that we did some years ago for the Connecticut DEP related to dioxins, and it was a 30-day sampling event using high-volume samplers and collecting 7,000 to 8,000 cubic meters of air. And then co-located samples out in the Gulf during the Deepwater Horizon event that occurred in 2010. And these, again, were co-located samples for dioxin sampling. Next slide. The first pilot study, and we did a number of them, that was conducted in December of 2019. The sampling location was near our office in Gainesville and was in Alachua, Florida, which is kind of a rural suburban setting. 24-hour and 72-hour sampling events. We used the Tisch TE1000 high-volume air samples. Air volumes resulting in 24 hours about close to 350 cubic meters, and then 72 hours would be almost close to 1,000, but from 935 to 974. SOPs were developed for the sampling and customized for PFAS. Each of these sampling events in the pilot were 3 co-located samples and a field blank, and each sampler had a glass fiber filter and a sorbent module in series. Next slide. This is a photo of the pilot study at Alachua, Florida, on December 2019. As you can see, the 3 co-located samplers. On the left, on the trailer hitch there, you see a meteorological tower that was used to get site-specific meteorology. We wanted to know wind speed and direction, ambient temperature, which you use to correct the air volume, and atmospheric pressure. Next slide, please. Blank results. I'm presenting these because blank results are very important. After this study, all filter blanks, including the 3-trip but 2 field blanks in the lab bank, were all clean at reporting limits of 1.5 nanograms for 30 of the 32 PFAS analyzed. The 2 exceptions shown in the bullet below were observed in the majority of blanks for GenX and 6.2 FTS. All sorbent blanks, 3-trip plus 2 field and 1 lab, were clean at reporting limits of 1.5 nanograms for 25 of the 32 PFAS analytes. The remaining analytes range from 1 to 12 nanograms in sorbent blanks. Next slide, please. As a result of this first pilot study, we were able to achieve the detection limits shown in this slide. Absolute nanogram quantities are on the left for all of the parameters of the 32 compounds shown previously, based upon 24-hour and 72-hour, so it's a function of the air volume that was collected. And you can see the range goes from the low picogram per cubic meter range for the majority of the compounds to up to 10 to 12 picograms per cubic meter, which is again influenced by the blank contamination. We found throughout all of our measurements that the blanks dictated detection limits. You know, you might be able to get better detection limits with more volume or with analytical optimization, but the blank contamination will preclude you from getting lower. And that's true of most of these measurements. We encountered it with our dioxin program some years ago that we did for the Connecticut DEP, and we were able to achieve detection limits in the femtogram per cubic meter, believe it or not, once we got control of contamination. Next slide, please. And then we took the method out into the field and conducted field sampling events at a number of locations. And these locations were all Eurofins laboratory facilities, so it was easier to get the cooperation from the host, obviously, doing that. And they were in Pittsburgh, Pennsylvania, King of Prussia, Pennsylvania, Albany, New York, Chicago, Illinois, and Milwaukee, Wisconsin. And these were all collected in the summer, June and July of 2020. Duration in hours, approximately 48 hours. Air volumes collected and range from 513 to 659. And reporting limits, again, were a little higher than the pilot study. Again, a function of contamination and also a function of air volume. They achieved about 2.5 picograms per cubic meter. Next slide, please. Here are some of the sampling events shown on the bar graph for the blank data. And the reason I show this, and these are absolute nanograms, not concentrations, this to show what you're up against with respect to contamination. We saw in all of the field blanks that were at each of the sites were contaminated to some extent. The majority of the parameters were below the reporting limits shown, but PFBA, PFOA, and NMFOS and NMTFOS had contamination that was detected on a regular basis. The only one that was an issue was PFBA and PFOA, but when you'll see the actual data, you'll see that these levels really didn't influence the reporting concentrations. Next slide. Here's the results from the pilot study in Alachua, Florida, in December 2019, and here we can see the two compounds that showed up most predominantly, PFBA and PFPA. So that's butanoic acid and pentanoic acid. Let me see. We have concentrations of over 100 picograms per cubic meter for PFBA at all of these locations, and these are 3 co-located samples. So we're looking at those samplers that were in that prior photo, and there are 3 in each 24-hour and 72-hour segments. The mean concentrations are shown on the right. So we're well above, in most cases, or approaching 100 picograms per cubic meter. And this is not unusual. If you look at data in the open literature, there was a study done by the Minnesota Pollution Control Agency, or their regulatory agency, that showed the most predominant the most predominant PFAS compound in ambient air is PFBA. Next slide, please. Next slide, please. Okay, here are the data from the sampling events in bar graph form that I showed previously for Albany, Chicago, King of Prussia, Milwaukee, and Pittsburgh. We have PFBA and PFPEA. Again, the butanoic and pentanoic acids are the most predominant species. As you can see, we have concentrations of PFBA that are the most predominant. And the PFBA is also found at higher concentrations, and these were not affected by the blanks. As you can see, in the case of PFBA, the blank contamination in the prior slide was like 10 or 12 absolute nanograms, and that's 10 or 12,000 picograms. And when you divide it by the air volume, it's not that significant. So this is the most predominant PFAS compound in ambient air, is the butanoic acid. And that's a function of its volatility, really. I don't know that it's a function of its ubiquity or a function of its unique nature as a member of the PFAS chemical group, but it's obviously one of the more volatile compounds and appears in the highest concentrations in ambient air. Next slide, please. Now I'm going to talk a little bit about passive sampling. Passive sampling is another technique. Chase mentioned it. It's been alluded to already by prior speakers. These are some sampling devices that I got courtesy of Environment Canada, Tom Harner, who does a lot of work with passive sampling. In fact, passive sampling has been used to collect most of the PFAS data internationally, particularly in Canada and Europe, where they've been looking at PFAS in the environment for a lot longer than the U.S., in fact. And here you have, in the middle of this photo, you have what looks like a flying saucer, or some sort of alien device is actually the passive sampling device, and it has assorbent media in it. Next slide, please. This is a close-up of what one might look like. This is one that we used in a study that was conducted for US EPA for PCBs and indoor air. Next slide, please. Here's an interior diagram of it. As you can see, in the middle is a foam disc, in this case polyurethane foam. You can hang this device. You can position it on a bench top or what have you. And the air basically is collected by a process called passive diffusion. There's no actual pumping done, no actual flow measured, but based upon published data, or if you run co-located samples that are being collected with a pump, you can come up with a passive collection device, passive device collection efficiency or method, and as a result, you can calculate the concentration of the PFAS in ambient air at the end of the sampling event. Next slide, please. This is a description of the sampling method. It's a Tisch model TE200 PAS, two-dome design as just shown. There were polyurethane discs, 5.5 inch in diameter, a depth of 0.5 inches, sampling rate of 0.8 cubic meters per day, and this is based upon a publication from Hazrati and Harad using the calibration of polyurethane foam disc for passive air samplers for quantitative measurement of PCBs and brominated diphenyl ethers. So you can actually use published passive collection data and to come up with an air volume, and when you have the total nanograms on the foam that's in the sampler, you can calculate a concentration. Next slide, please. And these are the samplers that we use in the study that I mentioned that was conducted for US EPA and indoor air at New York City schools, again for PCBs, but here's the same device that we would use for PFAS. And again, as I mentioned, there's no collection, no pump. You can leave them out there for as long as you'd like, for a week or a month or 24 hours or what have you. And obviously, as with the active samplers, the longer you leave it out there, the more you collect, and the higher the concentrations, or the higher the nanogram quantities that might be found on the disk. Next slide, please. PFAS are widespread in the ambient air globally. They're ubiquitous. These are some publications from a number of years ago showing the mean concentrations of total PFAS in air, all in picograms per cubic meter. And these are in some locations fairly remote. And I think what I'm about to say is that they're ubiquitous in the environment, as with many other semi-volatile organics or volatile organics. If you look for them, seek, and ye shall find. Next slide, please. This is a study that was referenced earlier by Matt, and this was work published by Barton et al. Back in the Journal of Air and Waste Management Association in 2006. And these data are shown here. They're adapted from Table 3 in that publication. We're showing measured concentrations only on a number of dates and note ND values. And they were comparing modeled concentrations to measured values. And the model tended to, in this study, over-predict the concentration of PFOA in ambient air outside the DuPont Washington Works in West Parkersburg, Virginia. And as I said, Matt talked a little bit about this study. This is one of the modeling exercises he referenced. Next slide, please. Okay, this is a very important slide. This was from the same study, the same data set. And what they did was they looked at particle diameter. I think they had a cascade impactor. I'm not sure what device they were using. And they basically measured the amount of PFOA found on each of the different particle fractions. And as you can see here, the highest mass percent of PFOA was found on particles less than 0.28 microns. And what this illustrates is that if you get these sorts of compounds that are going to be on the particles and on the very small particles, these particles behave almost like a gas in the atmosphere, and they can travel very long distances and be deposited many, many miles downwind from the source. And this is what we're seeing with a lot of the environmental contamination situations with PFAS in the atmosphere. Next slide, please. It's important to realize that soils are a critical reservoir for PFAS because of the methodology, or the process, I should say, of atmospheric deposition. They can accumulate in the soils, infiltrate in the soils, and then over time break through or leach through the soils down into the underlying groundwater. And that we've seen this in a lot of contamination scenarios with PFAS around the country. Next slide, please. Here are some data from the Parkersburg facility. Again, this is from the Ohio State University, and this is outside the Washington Works that I just shown in the prior slides, and near Parkersburg, West Virginia. And as you can see, they measured concentrations of PFOA in groundwater. And as you can see, the concentrations up to, in many cases, 10 kilometers away from, or 20 kilometers away from the source, they found measurable concentrations. The highest concentrations near the source, but as you got farther from the source, the concentration of PFOA was still in the groundwater, but at lower concentrations. Next slide, please. The state of North Carolina, and this is a study that was also referenced by Matt earlier, had a rainwater sampling program, and the purpose of this was to collect compounds, PFAS compounds, around the Chemours facility in Wilmington, North Carolina, and measure the concentrations in rainwater, which would be a good indication of what the concentrations would be getting to the soils. And these are both wet and dry deposition, obviously, since it's rain. And the rain will scrub out any particles that are suspended in the atmosphere. Next slide, please. This is GenX. They were focusing primarily on GenX in this studies around Chemours, because that was the principal compound of interest. And what this shows, this slide, is the GenX in rainwater in parts per thousand as a function of distance, parts per trillion, as a function of distance from the Chemours facility. These samples were collected in 2018. And as you can see, as you get from the facility up to a distance of 7 miles, they're still detecting measurable concentrations of GenX in the rainwater. And rather elevated concentrations, getting up as high as 810 parts per trillion. So again, this shows that the compounds, when they're emitted, because of the deposition properties, particularly if they're affiliated with particles, can travel great distances from the source. And not only travel distances, but be deposited on the soils and end up in underlying groundwater over time. Next slide, please. Again, here's another slide of the GenX in rainwater as a function of distance from Chemours. And as you can see, this is showing a gradient that goes up to 25 miles, and there's still evidence of GenX being found in the rainwater being collected by the state of North Carolina, And concentrations are smaller than the prior slide, but again, they're detected, and it shows the ability of the compound to travel great distances from the source over time. Next slide, please. Here are some data from PFOS in Lake Ontario, and this is old data, but I've got it here to illustrate another important feature, is that over time, the deposition into sediments and soils will increase the concentrations. And this is a slide showing the concentrations of PFOS. And as I told you, the Canadian and regulatory agencies were looking at the PFAS compounds long before the U.S. was involved. And these are sediments, bottom sediments in Lake Ontario, taken in 2006. They did dating on the soil sediments. You can actually date it using lead-210 or cesium or other radioactive elements to date the core. You section it, and then you find out the date that it represents, and then you analyze that section, and you can come up with the concentration over time. And as you can see, in this case, it's increasing from 1980 to 2006 up to 12 to 13. What are the units here? Nanograms per gram in the sediment. But the point of this slide is actually that over time, via deposition, wet and dry, particularly in this case, dry deposition, where the particles are getting to the bottom of the lake sediments, will be increased. And I would imagine that process has continued, and these concentrations are much higher than they were in 2006. Next slide, please. So, with some closing thoughts here on PFAS, in summary, the chemistry is extremely complicated, thousands of compounds, and it keeps expanding almost daily. They have very unique physical and chemical properties. They have both what we call a hydrophilic and a hydrophobic tail, meaning that they're water-loving and water-hating, to be simplistic, and they have both those properties. Their widespread long-term use has led to their ubiquity in the environment. They're literally everywhere. And they're in air now, as we're talking about today. Air emissions to the atmosphere can contribute to soil and groundwater contamination near and distant from the source. And everybody has seen that today. Active and passive sampling methods are available. Contaminant control is critical both in the field and in the lab. And if you work with the lab and they tell you they've never had PFAS contamination and they have it under control, then they're misrepresenting it. And EPA sanctioned methods are needed for sampling of ambient air. A TO method, I don't know where they are in development of that, but we need a TO method for sampling, and it might include an active sampling technique like TO13A, or it might involve a passive sampling technique. And I'm not sure where I am on time, but let's see.
It's about landfill gas emissions. Do we think landfill gas or other anaerobic digesters creating renewable natural gas might contain PFAS, given that they're typically based upon waste products, which often contain PFAS? So what maybe what you're seeing or thoughts?
Yeah, I'll take the first stab here for a second. We did look at a landfill, a closed municipal solid waste landfill here in the state of Georgia, and we were seeing some of the PFAS in that gaseous phase there, whether they were in the methane vent well, the vents that are coming up off of that, as well as a little bit in the soil, but it's preliminary for us. So they are possible. I haven't done anything further as far as studying that in greater detail, so I'll turn it over to Gary, whoever.
Yeah, there are a number of publications out there that show PFAS in landfill leachate. So it certainly would be obvious that it's going to end up in the air as well. So I think, and the fact that things have been deposited in some of those landfills for decades and decades, and the PFAS is going to still be there. So yes, I think it would be very, very likely that you're going to see PFAS in air emissions from landfills.
I think Liz, was it Steve from Sanborn Head? I thought he had a I think he had a publication from like maybe 3 or 4 years ago, where they had done some rudimentary collection of air, I believe, and found FTOHs.
Yeah, that's Steve Zemba.
Steve Zemba, thank you.
Yep. Okay.
I was just going to add that there have been a couple studies on ambient air quality above municipal solid waste landfills, and typically the fluorotelmer alcohols are present above what you'd see in, a city background concentration. So they're there in the air, and then there is a study out of Oregon State just recently which quantifies fluorotelmer alcohols in landfill gas.